Hi, everyone. Today, I would like to present our work on on-chain decentralized learning and cost-effective inference for DeFi attack mitigation. This work was done with my supervisor, Professor Balaji Pransomi, and Professor Prashant Krishmurthy from the University of Pittsburgh. So this work basically addresses a practical but an important problem, which is the real-time in-protocol detection is insufficient in the current DeFi ecosystem, especially focusing on the current state of DeFi. I'll start briefly by talking about the problem, then I will show why existing defenses are not sufficient. And then I'll present our framework, which is basically focusing on decentralized learning framework to achieve cost-effective inference on both layer 1 and layer 2 blockchain. So DeFi generally have experienced losses from logic and accounting vulnerabilities. These losses were reported by Rocket database to exceed 79 billion, and you can think of this number as a significant loss as a result of these attacks. There are many reasons why we still continuing seeing these attacks. Part of this problem is that we have limited tools. Most tools focus on static analysis before deploying the smart contract. So that's why we sometimes we see the same vulnerable smart contract is deployed by the same or different DeFi protocol on more than blockchain and get exploited simultaneously. So to mitigate the problem, let's talk about the limitations of the current tools. So as reported in the literature, automated tools can detect between 8 and 20%, which leaves the rest, which they call machine unauditable bugs. These exploits usually come in, these exploits basically exploit DeFi, basically focusing on the state of the DeFi itself more than the code bug. So this is what a usual vulnerable smart contract look like. If a vulnerability is identified by the attacker, then the smart contract will execute the attacker's instructions, basically because most of today's smart contracts rely mostly on external tools to monitor the blockchain. But there are problems with these external monitors, especially off-chain monitors. They are blind to private transactions. Most of them focus on the mempool, where all transactions queued in order to be included by miners or validators. So also, most of the current tools focus on finding every bug and fix that bug, where we have vulnerabilities come in transactions, and sometimes these transactions bundle multiple smart contracts and including the state of the blockchain to create an exploitable condition. So the transaction itself may look as a normal transaction, but it can create an exploit. What is worst is that today most of DeFi protocols do not have real-time in-protocol defenses that are dynamic interfaces that interface with the transactions themselves. So how to move from static tools to more adaptive methods in order to mitigate such attacks? So machine learning and deep learning have shown to be very effective in the context of general security, not only for detecting known attacks, but also to detect unknown or zero-day vulnerabilities. But machine learning, direct deployment of machine learning is challenging on the blockchain. So here, some challenges of on-chain machine learning, and of the obvious reason or the obvious challenge is the gas fee. So the training and the inference are the main challenges for a machine learning to run on the blockchain. Also, if you have, let's say you have a machine learning model that is running off-chain, if you deploy the same model on-chain, you may end up with totally different performances. This is because Solidity obviously does not support floating point. Now, our goal in this work is to provide a framework for real-time, decentralized, in-protocol DeFi exploit mitigation. So we design a transaction-based, decentralized framework that decouple the computation between layer 2 and layer 1 blockchain. Also, we isolate the computation in the inference layer itself. We also introduce proof of improvement, which is a very simple protocol that accept or reject micro updates that coming from decentralized nodes to preserve the model integrity from being poisoned. Our framework also introduces zero-cost inference, where you can deploy the smart contract once and use it for unlimited times using an off-chain provider. In addition to that, on-chain also a tier. So let's look at what we want at the end. So we want the machine learning to be running on top of the smart contract. So all transactions come into the machine learning model, get classified before it reaches the next state, or B+1, or block +1. So in a case if we have an attack, then the DeFi protocol decides if they want to reject, pause the smart contract, or just detect the attack itself. So here is an overview of our framework. I will highlight some components. So proof of improvement is a simple way to either reject or accept a micro update. These micro updates coming from the decentralized nodes, our assumption here is that the DeFi protocols will collaborate into training this model. Each proposal will be evaluated if it will improve or degrade one of the 4 metrics, accuracy, precision, recall, and F1 score. On layer 1, we have the inference, where the inference will take the weights from proof of improvement, and then it can perform either zero-cost inference off-chain or on-chain inference. Also, we have the DAO, which will check if proof of improvement, for example, misses an adversarial attempt into poisoning the model. So they will propose to roll back the model itself to the previous version, which basically will reverse the weights. So now let's talk about layer 2, layer 1 computation separation. So layer 2 blockchains are usually more cost effective than layer 1 blockchains. And we separate the training and the inference computation, as well as how the model is being executed in the inference layer. So for example, in CNN, we do not take the whole model and iterate over all the weights, but we segment or isolate each layer independently. Now for the weight propagation from layer 2 to layer 1, we use very simple approach, which is commit verify scheme. Our goal here is not to complicate the process because we don't want the gas fee to be substantial. So for the model consistency, again, if you deploy the same model on-chain that you have off-chain, you will end up with totally different classes. And again, the reason is that Solidity does not provide floating point support. So what we did here, since our goal is to guarantee that off-chain and on-chain model are exact replica, we use a simple way to scale weights as well as the features. So now I would like to talk briefly about our data. Since there is no comprehensive publicly available raw transactional data. So we had to create our data set, which basically based on from 8 EVM blockchains such as Ethereum, Binance Smart Chain, Polygon, etc. They are from 2020 till 2025, focusing on the features that can be observed by the smart contract during the execution time. So for the models, we don't want our framework to be tied into a single model. So we evaluated our approach on 20 different variations from lightweight models such as logistic regression, SVM, up to CNN and RNN with 10 layers. Again, we are focusing on features that are observed by the smart contract during the execution time. Also, we have looked at other metrics such as accuracy, precision recall, F1 score, which are standard metrics in machine learning. In addition to that, we looked at the gas cost, bytecode, update cost, etc. So for our result, I would like to, I know this table is kind of small, but I would like to highlight that the best performing model, even though our focus in this work is not the detection itself, but how to include machine learning directly into DeFi protocol. So CNN with 4 filters and 4 kernels achieved slightly above 90% accuracy. For the inference cost, which is important because this process is repeated over and over, for linear models, it ranges from 33K up to slightly lower than 60K of gas. For more complex models, it exceeds 1 million in gas. Still, this is, can be seen practical compared to previous literature. Again, querying the model off-chain will be always free of cost. For propagating model weights, light models such as decision trees, it was slightly lower than 100K. For more complex models such as RNN, still we are under the gas limit of Ethereum. Obviously, the update cost will scale as we increase the model complexity. Now, for the bitwise consistency between off-chain and on-chain models, we started to see the first 2 models, namely MLP and CNN, to be consistent when we scale the weights as well as the features to 10 to the power of 12. By reaching to 10 to the power of 14, we see all models were consistent. Now, for the inference throughput, for the on-chain tier, it was averaging around 11 classifications per second, which is close to the current Ethereum, which is 15 transactions per second. Now, we want the model to be resilient against model poisoning. So we want to see how proof of improvement will react when we feed the model with malicious updates. So if we look here, we can see accuracy, precision, recall, and F1 score. And if we focus on this specific metric, we can see proof of improvement stabilize the performance compared to unfiltered models. So in comparison to previous work, we compare our work with machine learning to smart contract, which basically a direct translation from machine learning to smart contract. Our framework outperforms machine learning to smart contract in terms of cost, inference, and contract size. Also, we compared our work with zero knowledge machine learning, even though it focuses on model confidentiality and integrity. Our focus is on the weights integrity, since we are assuming DeFi data are publicly available on the blockchain. So to conclude, we present to our knowledge the first transaction-based decentralized layer 1, layer 2 framework that can be used for real-time defense, such as intrusion prevention system or even intrusion detection system. We separated the computation between layer 2 and layer 1, as well as we introduced proof of improvement, which is a way for resistance, for adversarial resistance against malicious actors trying to poison the model. That's all for me. Thank you.
The talk. Do we have any questions?
Interesting talk.
Thank you.
Question for you is, did you find the model to work better for a certain type of attack? Like at a high level, maybe we can say there are attacks on the smart contract level, which is a exploit. There could be attacks from external perspective, like let's say Oracle attack. And then there are attacks that are more social based, like private key compromise. So based on this model, does it work better for one type versus the other?
This is an interesting extension. We haven't looked at these aspects, but certainly these are great suggestions to look at in the future.
So yeah, so I guess you mentioned L2, right? But assume you are assuming some kind of a honest majority or super majority assumption on those set of nodes who give you.
Yes, our assumption is that nodes that train the model are the DeFi protocol themselves.
No, but then do you want that when they do the computations for whatever F1 score or whatever, do you have assumption like there has to be honest majority among them?
Yes, they're supposed to be honest majority, but proof of improvement also can mitigate model poisoning attempts. It's not perfect, obviously, but it can also mitigate such attempts.
Interesting talk. I wanted to know, when you mean for DeFi attacks, how this relates to symbolic execution, like the properties from smart contracts, yeah, if there's an advantage.
Yeah, so the focus is basically on the transactions themselves. We're not going beyond into exploring smart contracts themselves, because there are a lot of literature looking at different approaches to detect vulnerabilities in smart contracts themselves.